It sounds pretty tough, pretty ominous. Monotonic functions in first derivative test. All it means is this. When we say monotonic functions, we're talking about either they're increasing functions or decreasing functions. How would you define a function is increasing versus how would you define it if it's decreasing? Yes, the slope. But what does the slope tell us? How do we get the slope? The way you determine if something's increasing, you're right. If we look at the graph, we know this is increasing. Why? Because as x goes to infinity, what happens to y? Y is increasing. This is decreasing because as x goes to infinity, the y values decrease. So at each x I pick, decreasing function is getting lower and lower and lower and lower. Increasing function, every x values I pick, as x gets bigger, the y values get higher. So the way you would define an increasing or decreasing function would be this way. X1 is less than X2, because we're talking about an increasing function. X is always getting bigger. Then f of X1 is also less than f of X2. That's an increasing function. Here's X1. Here's X2. There's f of X1. There's f of X2. So f of X1 is less than f of X2. And then likewise, so are the y values. Decreasing functions would just be the opposite. But the x's have to be increasing. X's are always going to the right. The reason for that is because if we have a motion problem, the x's are time. Time can never go backwards. So the x coordinates always go to the right. Then it's decreasing if f of x1 is greater than f of x2. F of x1 is up here, and f of x2 is down here.
The same thing. Why include that?
What's that?
For this one, f of x1 is decreasing and f of x2 is increasing. And here,
This just says f of x1. The first point is higher than the second point. This one says the first point is lower than the second point. The inequalities are different. This is how you can tell by looking at the values whether a function is increasing or decreasing. That's what we call monotonic functions. They're either increasing or they're decreasing. So if we look at also, this helps us. If we had a graph that looked like this, you're right. As you said earlier, we could talk about the slopes. The slope here is what? Is it positive or negative? It's positive. The slope here, positive or negative? The slope here, negative. It's going down. It says that the curve is continuous, but we have positive slopes here and negative slope here. The mean value theorem tells us, and the Rolle's theorem, that there has to be a point in between here where the slope is equal to 0. If it's positive here and negative here, then somewhere in between there, it has to be 0. That's how we can tell if it's increasing or decreasing. And we can do all that stuff with the first derivatives. Find the first derivative, plug in a point. If it's positive, it's increasing. If it's negative, it's decreasing. If it's 0, it's a vertex. All right, so let's look at example 1. Find the critical points of our function x cubed minus 12x minus 5. And identify the open intervals in which it's increasing or decreasing. Tell where it's increasing and where it's decreasing. So how do we do this? So what would be the strategy here? With everything we know so far, we want to know where it's increasing or with what we just talked about also. What would be a critical point? What would that entail? No. Don't read. I want you to tell me what you know. Why is that a critical point? Yeah, I know. If you read it, it's pretty easy to answer the questions. But why? Why is that a critical point? It's a critical point because at that point, we can determine by looking at points on both sides whether it's increasing or decreasing if that's a vertex. So it's a critical point because it tells us at that point something very important happens. Critical points could be asymptotes. Critical points could be zeros, could be x-intercepts. So in this case, so how do we find our critical points? We first have to find the first derivative. 3x squared minus 12. Then what do we do? Because we're looking where it's increasing, decreasing. Set it equal to 0 because we want to know where the vertex is. Add 12 to both sides. divide by 3. Square root both sides. So my answer equals what? No, plus or minus 2, right? That's why I put it on this side. Plus or minus 2. So we have 2 critical points. Because all we're looking here is where the graph's increasing, where it's decreasing. We know what happens at -2 and 2. What happens there? Where do these come from? Not intercepts. First derivative set equals 0 is what? Where is the slope equal 0? The vertex. These are vertices. The slope is 0. One of these is going to be maximum, one of them is going to be minimum. Relative or local. So how do we determine which is which? Whether it's going to be this is maximum or minimum? How do we determine that? Well, plug some points in. We have at -3, at 0, and at 3. We know here, at this point, we know the first derivative is equal to 0. It's a horizontal slope there. What happens at -3? Is it increasing or decreasing on that side? What do we do? How do we find that out? Plug in this value and the first derivative. So we get 3 times -3 squared minus 12. What's that? Because these are my critical points. I need to find what happens to the left of it. I have to find out what happens to the right of it. -3 squared is 9. 3 times 9 is 27, minus 12 is 15. It's positive. So on this side, it's increasing. What happens at 0? We get 3 times 0 squared minus 12 is -12. So here it goes down because it's negative. And at 3, 3 times 3 squared minus 12, 27 minus 12 is 15. It's greater than 0, so it's increasing. So this is a max. This is a min. So where is it increasing? Where is it decreasing? The question you had earlier, why we use 3, these are called test values. We have to know what's happening on that side because we know nothing happens here, nothing happens here. So where is it increasing? Where is it decreasing? Where? No. It stops increasing at -2, right? Because it's 0. So what's happening to the left of it? Everything to the left of it is increasing. So it goes from -infinity to -2. Where else is it increasing? So union from +2 to +infinity. That's where else is going up. And the only place it's going down is between -2 and 2. Why do we use open intervals? What? Oh, we can't use the endpoints because at the endpoints, the slope is 0. It's neither increasing nor decreasing. So we can't use the endpoints. So we have to use open intervals. So let's look what's happening here. The slope is positive, which means the first derivative of x is positive. And then it goes to the first derivative of x is negative. If it goes positive to the left, negative to the right, that means we have a maximum. It goes up, then down. So we have a maximum. If it goes from negative to positive, then we have a minimum. Negative means down, positive means up, so we have to have a minimum. All right, let's look at the next example. Well, I'll write that down for you. We have a maximum if the slope or the first derivative changes from positive to negative as x goes to the right. Because it was positive, then it goes to negative, so we have a maximum. We have a minimum if the slope, which is the f prime, changes from negative to positive as x goes to there. So from negative slope to positive slope, we have a minimum. And again, what happens here? It goes from negative to positive, and it's 0 in the middle between there. So if it goes from positive to 0 to negative, then we have a maximum. Example 2. Find the critical points of f of x equals x squared minus 3 e to the x. Oops, that was example 3. We'll go back and do two later. And tell me where it's increasing and decreasing. So what do you have to do first? Find the derivative. So we have f g f prime g prime. So we have x squared minus 3 e to the power x. The derivative of x squared minus 3 is 2x. Derivative of e to the x, e to the x. It's a product, so we add. So we have 2x e to the x plus x squared minus 3 e to the x. We can factor out an e to the x, which will give us 2x plus x squared minus 3. I don't need the parentheses, so I can rewrite those. Okay, we found the first derivative. We simplified it. Now what? Set it equals 0. Now, looking at this, what can you tell me about the right-hand side and making it 0? What's that? Nope. What does this tell us? Is this going to help us? Can this ever be 0? No. So the only part that's going to tell us what 0 is if we factor out these two guys. This is a quadratic equation. If you don't remember your factoring rule, use the quadratic formula method, which is negative b plus or minus square root of b squared c over 2a, where a, b, and c are the coefficients. But in this one here, we can factor out. Since the second sign's a minus, that tells us the signs are opposites, and the bigger number gets the plus. So what times what is 3? When you subtract them, you get 2. What times what equals 3? When you subtract them, you get 2. Very good. 3 and 1. So the bigger number is a positive. So this function equals 0 when x equals negative 3 and x equals positive 1. Those are my vertices.
What's the critical point? X negative. Are they critical
Those are
points?
my critical points. Yeah, that's what I'm finding. Those are the critical points are what makes this equal 0. Those are the points those are the ones that make me look for something now.
Must it equal 0 for it to be a critical point?
Yes. Or undefined. Because the reason why it's set equals 0, because any other value is irrelevant. 0 tells us that we have a vertex. All right, so at negative 3 and 1, where is the function at negative 3? We know we have a vertex, and 1 we have a vertex. So where is it increasing? Where is it decreasing? What test points are you going to take? These are my critical points. -4, 0, and 2. You have to take them everywhere around it. So what happens at -4? Okay, we know e to the x will always be positive. So we don't have to worry about that. All we're looking for is a sign. We don't care about the numbers. If we put in -4, is this going to be positive or negative? E to the x will always be positive. So it has no x-intercepts. So let's look at the factor part. If we put -4 in there, -4 plus 3 is -1. -4 minus 1 is -5. Negative times negative is positive. So this side's going up. At 0, 0 plus 3 is 3. 0 minus 1 is -1. 3 times -1 is negative. So it's decreasing here. So at -3, we have a max. At +1, we have a min. And at 2, 2 plus 3 is 5. 2 minus 1 is 1. So it's increasing. It's positive. So that tells us our function is increasing from where to where? From -infinity to -3. And where else? And then from 1 to infinity, right? It's the critical values that it's the critical points that are endpoints. And it's going down between there from -3 to +1. Very good. All right, let's look at example 2 that I skipped by mistake. Find the critical points of x to the power 1/3, x minus 4. Yeah, so on the last one, the critical points were at -3 and 1. This is where the vertices are. So what about here? So this is x to the power 1/3. This is x minus 4. The derivative of x minus 4 is 1. The derivative of x to the power 1/3, power -2/3, which makes it 1/3 cube root of x squared. Yes.
The last example you did on chart section 1, you with the x squared, you plug in the values into the original function, the f of x, and
Yes.
the derivative. So why would that?
Yes, because in section 1, we're looking for maximum minimum. The maximum minima are determined, the values are determined by the f of x. F prime of X simply tells us whether it's increasing or decreasing. So in section one, we were looking for the actual values. What numbers are the maximum minima? This one here tells me where is it increasing, where is it decreasing? So F prime of X equals 1/3 cube root of X squared times X minus 4 plus cube root of X. That's what that one says. Okay, before we do anything, we have to combine these two terms. We have to get a common denominator. So I got to multiply 3 cube root of X squared, top and bottom. X minus 4 plus 3 X cubed. Okay, this is where you have to think of this now. Cube root of X times the cube root of X squared. They're the same roots. So we can multiply inside there. X times X squared is X cubed. So it equals X. So we have X minus 4 plus 3X over 3 cube root of X squared. X plus 3X is 4X minus 4. There's my derivative. So my critical points. Two conditions apply here. Critical points are where the first derivative is equal to 0, and they could be where the first derivative is undefined. So where is this function equal to 0? If we set this equation equal to 0, where does that happen? Yes, it only happens when the top is 0. So set the top equal to 0, move the 4 over, and divide by 4. So X is equal to 1. So that's one of our critical values, our critical points. The function is undefined when the denominator is equal to 0. And the only place that happens is if X is equal to 0. Those are my two critical points. We have an asymptote here. It's a vertical asymptote. And we have a vertex here. So what is the graph going to look like? The only number we can't use is this one. This is going to be our either a max or min. So let's pick a number here. Let's pick a number here. We just can't use this one. And let's pick a number here. See what happens. Because since the only vertex we have is here, that's the only place that's the graph is going to change. So what happens at 1/2? So on the bottom, it can never be negative. The bottom can never be negative. Why? Because x is squared. Once you square it, it becomes positive, and it's always going to be positive. So the only negative can happen is on the top. If x is 1/2, so 4 divided by 2 is 2. So in this one, this gives us a negative answer. So it's going down. What happens at +2? It's going to be positive. So it's going to go up. So this is a min. And on this side, at -1, actually, in everything beyond here, it's always going to be a negative slope because -4 minus 4 is -8. So it's always going to be negative. It's always decreasing. So everything on the left-hand side of this vertical asymptote is negative. So it's increasing where? It's increasing from 1 to infinity. It's decreasing from -infinity to 0. And from 0 to 1. It's decreasing. Your endpoints in these intervals have to be your critical points, unless they're in infinity. Now, the rest of that question is asking, find the function's local and absolute extreme values. How would we do that? How would you find the local and absolute extreme values? We know this is a min. Is it local or absolute? It's local. It can't be absolute because this whole left side is always going down. So as it gets closer to the vertical asymptote, it's going to be going down forever. So there's no absolute minimum. This is a local minimum. Do we have a local or absolute maximum? No, because this is an asymptote, so the graph will look something like that. And this part goes on forever, so there's no maximum, minimum, maximum, absolute or local maximum. No maximums at all. Okay, well, that end for that one. And that does it for that section.